everyone. In this video we're going to look at the derivative, so introduction to the derivative. Even though you've done it in units 1 and 2 maths methods, we're going to look at it again. So just a quick summary of what we're going to learn. So understanding that the derivative is also the gradient of a function, so it can be called the derivative function or the gradient function. Substituting in a value of x gives you the gradient at a point, which is also known as your instantaneous rate of change. We'll talk about that in the video. And we'll also talk about how to find the gradient of a tangent line. So a tangent line is just a line that has the same gradient as the point. All right, we'll cover that in a second. Not in a second, but in this video. All right, so for your bound reference, just make sure you know how to find the derivative. We're not going to do anything too complicated, but if you do come across a question that you think, oh, that one's a bit tricky, I should probably add that to your bound book, then add it to your bound book. And we're also going to go over the tangent, what it means by tangent, and then we've got some questions to practice. And if you need extra support, you can watch the Ed Rollo video. Or just watch the Ed Rollo video and this one at the same time. Not at the same time, but you know what I mean. Do them both. The more you know, the better you're going to be. All right, so what is the derivative? So let's think about, all right, we're going for a Sunday drive. Maybe you're on your learners and your parents are like, let's go out for a drive. So you're driving along the Peninsula Link. All right, we're heading down maybe to Dromana, beautiful Dromana. Now, on the Peninsula Link, we have what's called point-to-point speed cameras. So let's think of this curve here as let me just highlight it, as the speed we're going as we're traveling along the Peninsula Link. Now, what I mean by point-to-point speed cameras is that they're a little bit different to ones that you see set up on the side of the road, or even in a car. You know, you see the car parked, it's usually a four-wheel drive or a station wagon, and you see all the equipment in the back and you're like, oh gosh, there's a speed camera. On the Peninsula Link, the point-to-point speed cameras just mean they take your speed at one point, so let's say it's A, and then take your speed at a second point, B, and then do the average. So what it is stopping people from doing is not just slowing down when you see a speed camera, you actually have to be slowing down between those 2 points. Because if you see a speed camera and then you're like, oh gosh, I'm free, I can, you know, the speed limit's 100 and you might speed up a little bit because you're late for your picnic on the beach, then it takes it at B, so you're still going to get caught if you're speeding in between. So that's how to, you know, you're stopping people from, I guess, just slowing down when the speed camera is there. They've actually got to slow down the whole time because they have got to do the speed limit, because if they do speed, they're going to get caught. All right, so think of it in terms of that. So blue being the speed and the 2 points, all right, are the speed cameras, and that red line is going to be our average speed. And that is the average speed is our gradient, all right? So the gradient of this straight line from A to B is our average speed. So also known as your average rate of change, which is also known as, you might look at that formula and be like, oh my gosh, not another formula, but it's just your gradient formula. So if I write gradient there, excuse me, and you're used to seeing y2 minus y1 over x2 minus x1, which is just your rise over run. All right, you've seen that since probably year 8, definitely year 9. All right, so your gradient is just your rise over run. And you're like, well, why haven't we used y2 and x2 and y1, x1? Because we're using function notation now. So we're moving away from using x and y and using x and f of x. All right, so using that type of notation, which is extremely important. We've just finished transformations, so you can see why it would be better to use function notation as opposed to just x and y. So if I've got point A, so you can see point A here on our graph, then the corresponding value is f of A. So we're used to seeing that as x1, y1. And then we've got our second point, which is at B. So our corresponding y value is f of B. and that's just x2, y2. All right, so instead of using y2 minus y1, we've got f of b minus f of a. Instead of using x2 minus x1, we're using b minus a. All right, so it's rise over run, nothing new. All right, so the derivative function relates to the gradient. So just remember that, because you're going to have to calculate the gradient quite a bit. All right, so let's have a look now at this business here. And I've got a diagram on Desmos which explains it quite well. So we've got a parabola, all right, it's x squared, and we've got points P and we've got points Q. All right, so P is at A and A squared, because when you substitute A into your function, you get A squared. Then the difference between P and Q, so the distance here, is just H. So as H gets closer and closer to this point here, this line is going to give us what we call the tangent line, the gradient of the line at that point. All right, so that's basically your derivative at that point, and it's also known as your instantaneous rate of change. So in the previous slide, we looked at the average rate of change. If we're finding the derivative at a point, then it's your instantaneous rate of change. So think about it as your camera on the side of the road as opposed to your point-to-point cameras on the Peninsula Link. All right, you're doing it at a certain point as opposed to doing it over time. All right, so let's have a look at a diagram on Desmos. So here we've got our function x squared, which is our red one, and I've got a point here on the graph. All right, so I can just move that around. So I might put it back here at 2, 4, just because it's easier to see. All right, so that dot there, let me just go down, is a point, all right, on the curve, and this is going to be H. So as I move H, you can see the line, that blue line, moving. All right, so basically that line is parallel to the line going through the two dots. It might be a bit hard to see now, but as I move that point closer and closer to this dot here, oops, it'll disappear because H is the difference between the 2 points. So if it's 0, then you're dividing by 0. So we're just going to go. So as I move it closer and closer, you can see that this blue line is actually the same as the gradient of this point. Now, I wish I could show it as a tangent line, which I can't, but maybe I'll do that later on. But just pretend that, and I shouldn't ask you to pretend, but this blue line is the same, the gradient of this blue line is the same as the gradient at this point. All right, so that's what the instantaneous rate is. So as we get close, as this purple dot gets closer and closer, all right, so at this point, we're just doing the average rate of change between the 2 points. So we're still doing the average rate of change, but my value of H, if you look over here on the left side, it's getting smaller and smaller. So see how it's getting closer and closer to 0? So as it gets closer and closer, we are reaching our instantaneous rate of change. All right, so it's going to get closer and closer to 0, but never going to hit 0. So that's the whole concept of the derivative at a point. So you go from doing your average rate of change from point to point to the instantaneous rate of change at a point, all right, which is the same as the gradient of this line here. That's basically what your tangent is. All right, I'm just trying to see if it's got the tangent. So maybe I might just pause and see if I can do the tangent line for you. All right, so that red line, it would be good if I did it in a different color, is our tangent line. So see how it's parallel to the blue line? So they have the same, it's close to parallel. I'm not going to get it perfect because our value of H can't be 0. So pretty much parallel. So your tangent line will go through this point, 2, 4, and the gradient of that tangent line is the same as the gradient at this point. And you can see it's the same with the blue. All right, parallel. All right, let's move on. Let's get stuck into some actually calculating the derivative. Otherwise, we'll be here forever. So for each of the following, find the derivative with respect to x. So what we do when we're finding the derivative, we just take our power, reduce it by 1, and then move it to the front. Actually, let me show you. So if we've got x to the power of 5, the derivative, which the notation is d dx, we take that power out the front and then reduce the power by 1. So it becomes 5x to the power of 4. Now, if we have a longer expression, let's say like h, so we've got 6x cubed minus 2x squared plus 4x minus 6. All right, we just do each term individually. So your derivative, so we do 3 times 6, which is 18, reduce your power by 1, and then we do the next term. So 2 times 2 is 4, reduce your power, then 4x just becomes 4, and any constant will just disappear. All right, so it becomes 0. So 18x squared minus 4x plus 4. Now on your calculator, if you want to check your answer, you can just go to, all right, this one here. There's other ways you can do it, but I'm just going to show you here. All right, so d dx, and then we can put in our expression. So 6x cubed minus 2x to the power of 2 plus 4x minus 6. All right, and then you can check your answer there. So 18x squared minus 4x plus 4. So you can also do your derivative somewhere up here. So you can do it there, and this is good because it can do the derivative at a point, which helps you find the gradient at a point. So remember for the one I did on Desmos, which the expression was x squared, and we were looking at the point x equals 2. All right, so my gradient is 4. So if I go back to Desmos, all right, notice how I had the gradient of 4 here. All right, that's the gradient at that point. All right, let's have a look. So the derivative and the tangent. The derivative is also known as a gradient function. It tells us that the gradient at any point of the graph. Okay, so we just did that. To find the gradient of the tangent line, just find the derivative and then substitute the value of x into your gradient function. Which is pretty much what I just did. But I did on the calculator. Let's do it by hand. All right, I'm just going to do question 3b. So make sure you have a go at doing the other ones. These are all taken from your textbook, by the way. Pretty sure probably 9b, these ones. All right, so for the curve determined by the rule, find the gradient. All right, so we're using this notation f of x, so your derivative is f dash x. All right, so we use that notation for the derivative. All right, so that 3 multiplies the negative 2, so it's negative 6x, and we reduce the power by 1, minus 6x plus 2. Now, we only that y coordinate doesn't matter, it's just the x one, so we're finding it at 2. So I just substitute in 2 into my equation. All right, so 2 squared is 4. Negative 6 times 4 is negative 24. 6 times 2 is 12, so minus 12 plus 2. So that's going to be negative 36, negative 34. So on your calculator, let's just quickly check. All right, so we can just go calculation diff, and we want to do derivative at a point. So our expression was negative 2x cubed minus 3x squared plus 2, and we're finding it at x equals 2. Oh, did I do wrong? Negative 36. Oh, did I do? Whoops, that plus 2 shouldn't be there. Sorry guys, hopefully you recognize that. All right, I'm just going to keep that in the video. Sorry, so the constant, any constants just become 0. So I might just add that there, so plus 0. Sorry guys, hopefully you recognize that. You're like, no, you're doing it wrong. Yeah, so just making you aware of that error. All right, so this one I might do in a separate video, but just because I want you to get a bit of an understanding. So I might do the tangent and this later on. I'm just wanting to focus on questions on the derivative for now, and I'll do a separate video for the tangent, just to get you back into how to do the derivative. Yeah, so we'll leave question 10. I'll do that in a separate one. All right, so here we're going to find the derivative of a function that looks a little bit different. So this is from 9c. So 9b is your straightforward finding the derivative until you get to the tangent stuff here, like with the angle. I'll explain that in a separate video. I'm just conscious of time. I don't want this video to go for too long. All right, so what we can do is rewrite the expression just so we don't have that z squared on the bottom. So z squared is the same as z to the negative 2. All right, if we're putting it on the numerator, and 2z squared minus 4z. And then I'll go through and expand this. So we can expand just, like that. So z to the negative 2 times 2z to the power of 2. So that 2 is going to stay there. And then we're doing z and we add our powers. So negative 2 plus 2. And then we do the same to the negative 4. So it's going to be negative 4z negative 2 plus 1. So when you're multiplying the same bases, you add your powers. So the first one's going to end up as 2z to the power of 0. And then we're going to have minus 4z, negative 2 plus 1 is negative 1. All right, so a bit tricky there. I've chosen a tricky one. All right, z to the power of 0 is 1. So we still end up with 2. And then we've got minus 4z to the negative 1. Now, all I've done so far is just find the expression. All right, I'm just changing the expression so we can find the derivative. So our derivative, which I'm going to write as d dz, because our variable is z. All right, doing each term separately. So 2 becomes 0 and negative 4z to the negative 1. So that negative 1 multiplies the negative 4 to become plus 4. And then we reduce that power by 1. So it becomes negative 2. So we just end up with 4z to the power of negative 2. You can leave negative powers there. That's fine. If you like, you can also write it as this. But remember, every time you go a little bit further, you might be more prone to make errors. I have seen some students do 1 over 4z squared. All right, this negative power is not associated with the 4, so the 4 has to stay up the top. So I would just leave it with a negative power, but also showing you there just in case you had to transpose it. All right, so just to check our answer. All right, so we can do dz. We can use x if you like. Just make sure that you go, whoops, wrong button. You go back and write your answer in terms of z. All right, 2z to the power of, whoops, I wrote x, 2z to the power of 2 minus 4z all over z squared. All right, so we get 4 over z to the power of 2, which was the second one I had. So other ones in here, so b is the same, just bringing that z to the negative 3. C, you don't have to do any rearranging. You also do with D and E. Just with F, this term here is 6x to the negative 1. All right, and then you're going to have minus 3x squared. So this is from 9C. So if you need to look at the work solutions, you can have a look at the work solutions there. All right, question 8. Find the x-coordinates of the points of the curve at which the gradient of the curve is 5. All right, we might be getting into some tricky territory here, but we might do it anyway. And then we've got one more question. So I'll do these 2 questions, but please take note, we're just having an introduction to differentiation. So after this video, I will revisit this again and look at some more, some harder questions. So you'll be fine with 9B. It's just revising the basic derivative that you would have done in year 11. This is a little bit harder, but I think nothing beyond which you can do. All right, find x coordinates of the point of the curve. All right, so let's just rewrite that. So x negative 1 comes up the top, and then we've got x squared minus 1. All right, and let's just expand that. So we add our powers. You can probably do that in one go. You don't need to write it out, but I want to write it out so you can see where it comes from. Negative 1 plus 2 is x to the power of 1, and then we've got minus x to the negative 1. All right, so when we're using y equals, the notation we use is dy dx. So for x to the power of 1, we multiply by 1 and then reduce our power. And then same for the next one. So negative 1 times negative 1 is positive 1. So it's positive x to the negative 2. So just be careful when you're reducing your power from using negatives, that you go from negative 1 to negative 2. All right, anything to the power of 0 is just 1. And then we're going to have, we'll just leave it as negative 2. Or it's the same as 1 over x squared. All right, you might get that on your calculator. All right, so this question's a little bit different. It's told us that the gradient of the curve is 5, and we have to find the x coordinates. So all this is saying is, all right, dy dx, is equal to 5. So 1 plus x to the power of negative 2 is equal to 5. Now, I'm writing on this screen without it flat, so that's why my handwriting is very messy. All right, so we're just solving x to the negative 2. All right, so take that 1 over, so it's going to be 4. And I do prefer it like, let's just write it like this. All right, so 1 over x squared equals 4. Oh, actually, I probably could have done it a different way. All right, that doesn't matter. So 1 over x squared, what I can do is take the reciprocal of both sides. So I can change that to x squared is equal to 1 over 4. And, or actually, no. Sorry, I'm just thinking as I go. All right, and then I can rewrite that 4 is to the power of 4 to the negative 1. This is probably a long way to do it, guys. And then that 4 can be rewritten as 2 squared. Actually, no, I'm going to go back, sorry. I was doing it one way using the index laws, but I think I prefer this. So x is just going to be the square root of 1/4. And just make sure you do the plus or minus. So when we take the square root, we take the square root of the numerator, which is 1, and the square root of the denominator, which is 2. So x is going to be negative 1/2. And x equals positive 1/2. All right, which you would have got if I did the other method, but I think this is probably a bit easier to understand. So we've got this function here. All right, it does say the x coordinate, so that gives a hint that we needed to find more than 1, and that's because when we take the square root, we get both the the positive and the negative. All right. Last question we'll do in this video. So the gradient of the curve, blah, 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 at the point, blah, 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 find the values of A and B. All right, so let's just write down what we have. So I'm going to rewrite this with the negative power. So x to the negative 1 plus bx squared. And now I'm just going to find the derivative. So dy dx. All right, so we multiply the coefficient by the negative 1, so it's going to be negative ax, and we reduce the power, so it becomes negative 2, and then this is going to be 2bx to the power of 1. All right, so we know that the gradient of the curve at this point is 7. All right, so we've basically got two unknowns, our A and our B, so you need two pieces of information. So this 3, 6. All right. So let me just, so we can sub in 3, 6 into our initial equation. So we got 6 equals a times 3 to the negative 1 plus b times 3 squared, because it's telling us that that point is on this graph. All right, the point is 3, 6 is on this point, on this graph, and the gradient at this point is 7. So when x equals 3, dy dx is equal to 7. So we can use this information to get a second equation. All right, so dy dx is 7, and let's just substitute in 3. Now I'm just thinking we could probably go on to solve this by hand, and I really want to, but I think it might just get a little bit too messy. 7 equals negative a over, so that's going to become 9 plus 6b, and tidying this one up is going to be a over 3 plus 9b. All right, so you can go on. I'm just for, to make sure we save some time, I would rearrange this to get a on its own, and then, because they're just simultaneous equations, here's one equation, here's the other one. So you can solve them as simultaneous equations. They're a bit of a pain probably to do, but just get this as a equals, or you could get it as b equals, and then just substitute it into the other equation. Because we got to that point, I'm just going to use solve. Actually, I'm not going to use solve. I'm going to use this other method of solving. Where is it? This one here. So I'll show you just putting this one in. All right, so negative a over 9 plus 6 times b. You can use x and y in place of a and b. Just be careful not to get them mixed up though. And then the second one is 6 equals, let's get our fraction up, a on 3 plus 9 times b. And then we're solving for a and b. So a comma b. Now I've got to look at what I did wrong. A comma. No, there we go. That should have been a plus. Silly me. Just make sure it was meant to be a plus. There we go. So a equals negative 9, b equals 1. So if you went on to solve, and I'd have a go if I were you, trying to solve that by hand to see if you can get the a and b that way. I'm going to show you another way of doing it on your calculator. All right, so we've got this function here. So I'm just going to define that. Might not have to define it, but I am going to. And I'm just going to use f of x as opposed to y, because when we're defining a function, it's better to use f of x. All right, so a over x plus, now when you're using two letters together, make sure you use a multiply sign. So you'll probably notice me do that. So a over x plus bx squared. All right, remember we've got 2 bits of information. So this first bit of information, we've got the 0.36. So that just means f of 3 is equal to 6. Which is what I did here. All right, I substituted it in, but on my calculator, I don't need to do that. So when I'm solving my equations, I can just say f of 3 is equal to 6. My second bit of information is when my derivative is at x equals 3. At that point, it's equal to 7. All right, so there's our second bit of information. So all I need to do on my calculator is that. I don't need to go through and calculate the derivative. I can just use that function notation, and you'll be using that a lot with other questions. So I encourage you, when you're doing textbook questions, to have a go at practicing using your calculator as well. All right, so we're doing, just like I showed you before, the derivative at a point. So my expression, we've already defined as f of x. Sorry, let's put that in, derivative at a value. So f of x, and we're doing it at 3. All right, so we're putting that in. The problem is you get this error and you think, oh my gosh, I've made a mistake. You actually haven't. The calculator just doesn't like it. So leave it there. All right, so here's all the working out that we want. And we just let it equal 7. All right, so just ignore that error message because we want all this working out there that they've done. All right, and we're just going to let it equal 7 because your derivative at x equals 3 is 7. Told us in the question. All right, there. All right, let's go back to the calculator. And we're solving, remember, for a and b. So we go a comma b, and there we go. So if you were doing this by hand, I don't think you'd probably get one with annoying numbers because it's quite time consuming, but just rearrange and solve, using simultaneous equations. On your calculator, so easy to do. You define your function. You've got 2 bits of information. So the 0.36 is on your curve. You substitute that into your original function, not into your derivative, because this 6 is equal to y, not dy dx. So make sure that you don't get confused between those two. Then to get your derivative, we can put all that in. You can do that separate and then copy it in if you like. You don't like that error message, but just ignoring the error message and let it equal 7 because it told us that the gradient is equal to 7 at x equals 3. And then we get the -9, 1 from there. All right. As I said, I'm going to do a separate video for the tangent line just because, yeah, it's 9. You have class in 20 minutes and I don't want to go over time. And I don't want to overwhelm you with the first video. So see you guys.